disruption. Let's get going. So I think, first of all, a key thing about AI, we'll come on to what is AI, machine learning and deep learning specifically, but it's very driven by data. Data is key. And we have an expression in machine learning and deep learning, garbage in, garbage out. So the quality of data is really important for training, for performance, accuracy. And big data has really been driving the growth of AI. And as I said, we'll come into the definition of AI, machine learning and deep learning. But essentially, modern AI is machine learning and deep learning. It's narrow AI. It is focused on a specific task. It is not sentient intelligence. It doesn't think. It isn't like AGI, which is in the movies, which is Terminator, etc., and Skynet. We don't know when that will come. It could be in 10 years, it could be in 50 years, it could be 100 years or never. But the current AI we have today is not AGI and is not going to be AGI. It is really data-driven. It is really relying on numbers, statistics, and understanding patterns and data. And as you can see from this slide, the growth in the internet, the growth in social media and mobile traffic has really been accounting for this dramatic explosion in data. IBM have a statistic that 90% of the data created in human history was created in the last 2 years. And that's going to continue to grow. And why is that relevant to cybersecurity? Well, the deluge of this digital data is, of course, creating risks as well as opportunities. And so the volume and velocity of data is a deluge of data, and the devices that are coming on in stream going forwards are accelerating that trend, meaning that there are more opportunities for cyber criminals. But it's really, excuse me, a data-driven world. What are the current challenges we have with cybersecurity? Well, ISC squared point out there's 4 million plus shortage gap in skilled cybersecurity experts, and that's set to go to 6 million on the forecast by 2022. It's also a very costly area. It's costing, expected to cost about $6 trillion by the end of 2021, the end of next year, this whole area. 80% of CEOs, according to PwC, have cybersecurity as one of their biggest threat, or one of the top 2 biggest threats, and view it as an area where they have, again, skill shortages. AI is a tool that can augment cybersecurity specialists. I'm not proposing it as something to replace them, but it can help plug that gap, and it can help go through that big data that we're facing, that high velocity and volume and veracity of data, and try and make sense of it and identify malicious patterns of malware before they infect and spread. And the era of 5G that we're going to talk about, and IoT, Internet of Things devices, are going to accelerate this and increase the vulnerabilities going forwards. When we talk about IoT devices, we're talking about devices that are connected to the internet. And with 5G, 5G, we'll come on to in a second, is going to help accelerate this, and we'll go into the reasons for that in a moment. But you can see this diagram based on data from Statista, which shows that by 2025, there's going to be 75 billion plus devices connected, IoT devices, and that's about 9 per person on the planet. So this huge explosion of connected devices with machine-to-machine communication, and then the amount of data that they're going to be generating is going to go up even more exponentially than it has done in the last 2 or 3 years, which in turn means that we're going to need more machine learning and deep learning, and in fact AI, to make sense of this data, to analyze it, both in terms of the services that we provide, be it healthcare, be it connected cars, autonomous cars, which may take a bit longer to come, and other things, our mobiles, etc., but also in terms of cyber security, because the velocity to spread malware through this and the ability to spread it through larger volumes is going to increase through the devices, and we'll come on to that in a moment. So there's going to be this interaction between 5G, the 5th generation of mobile, which is only in its embryonic stages right now in spite of all the hype. It's going to take a couple of years really to properly build the networks, to scale them for standalone 5G networks. But it is going to be dramatically faster than 4G in other previous generations. and not only faster, but much lower latency, depending on who you believe, 1 millisecond to 4 milliseconds, which means that you can start to do things like remote robotic surgery. So for example, as David pointed out, the efforts that China are making, well, in China, they've already conducted remote robotic surgery with 5G, or brain surgery where the surgeon was 3,000 kilometers away from the patient. That is the kind of thing that 5G will enable. Ultra low latency, but also exponentially greater device connectivity. Every square unit, for example, square centimeter or square millimeter, you can connect 1,000 more devices than you can with 4G. All of us who are on 4G will often notice the network is maxed out. It often has problems, latency, or drops to 3G. 4G networks pretty much globally are maxed out. And that is another reason we need to move to 5G. It can handle exponentially greater number of devices with significantly lower latency. That in turn is going to facilitate something called edge computing. Edge computing is where the data is processed closer to where it's created. Right now, the cloud servers are very hot, and that's where most of the data sits, big data lakes, big data, the intelligence, the AI, the machine learning is taking place on the cloud server. In the future, in this 5G architecture and with edge computing proliferating, we're going to have intelligence on the devices all around us. Already, it's forecast that by the end of this year, there'll be about 190 million smartphones with AI chips on them, i.e. edge computing. By 2023, that's expected to reach 1.25 billion. So it's not just mobile devices or mobile phones that will have AI embedded on them. It'll be smart sensors, security cameras, internet-enabled fridges, etc. And when they do come, autonomous cars, etc., drones, and many healthcare devices are going to have AI on the device itself and communicating with each other. So we're going to be increasingly working with intelligent devices where the data is being processed there, and that means you've got less traffic going back and forth between devices and servers, as you might do right now, because and the server will be used in a hybrid system, a hybrid cloud edge system for training AI and for storing historical data. However, on the one hand, there are some cybersecurity analysts who say, well, that means that there's going to be less traffic to hijack. But the flip side is the device then becomes the vulnerability point and one that can infect the system and spread malware all over the place. And unfortunately, as we know from, for example, the MKAI botnet attack in 2016, that devices have been pretty poor, or manufacturers of devices have been pretty poor in embedding security into them. Let's do a quick overview of AI. AI is an umbrella term which refers to computing systems that are capable of performing tasks that humans are very good at. And a key area is that we're going to focus on rather than classical AI, which is more, black and white, deterministic, and didn't really scale well in the real world. We're going to focus a lot on machine learning and deep learning, which are the modern techniques that are being used. So AI is the overall umbrella term. Computing systems which are very capable, or which are capable of performing tasks that humans are very good at. But then we come to machine learning, which is a field of AI that applies statistical methods to enable computer systems to learn from the data and stress that the data towards an end goal, which was actually introduced by Arthur Samuel in 1959. But machine learning really started to take off in the 90s and early 2000s as data started to become available and the classical AI systems kind of fell away. Deep learning, which is responsible for a lot of the breakthroughs in AI that we've seen over the last decade, in particular since 2012, is a technique, is a subset in turn of machine learning, in turn a subset of AI. It relies on neural networks with several hidden layers, and they're referred to as deep neural networks, and that's where a lot of the breakthroughs in AI have been occurring, including deepfakes, which is part of GAN's generative adversarial networks. This is an example. I put this to grab this whilst the previous speaker was on, just to put a quick overview on the previous two speakers of AI, of what deep learning is, and convolutional neural network, which are often also used in GAN's generative adversarial networks that generate deep fakes. So you can see you've got an input here, and on the left-hand side, it goes into a convolutional layer with something called ReLU, which is a mathematical function, a statistical function, rectified linear unit. And then on the right-hand side, you've got a probabilistic distribution of softmax, which is then saying, what is that image, and ranking it statistically. But what happens in the training is it goes from left to right recursively, backwards and forwards, until you get to low loss, until your losses converge in the network, i.e. you've got to high accuracy levels. So whilst there are other machine learning techniques which are not black boxes, this is often referred to as a black box because you could have millions of neurons in here and you don't know what each one is doing, although you can actually put saliency maps here on the right-hand side, or heat maps, to understand what it's looking at on the output layer. And we actually do that in medical imaging, for example. So you can actually then alert the doctor how the deep neural network made its decision. But we won't go too much into that today. This is what the output looks like of a convolutional neural network. So this bounding box is then recognizing what a person is. Why do we use deep learning? As Andrew Enge pointed out, the bigger the data sets get, the more deep learning neural network will outperform older algorithms. But it isn't always the best tool to use if you haven't got sufficient data. Then there can be cases where other machine learning algorithms are actually better to use. Now, coming back to our 5G networks and the potential malware attacks and devices, this is actually an image I've taken from Juniper networks. And it shows in this environment here, the devices on the left-hand side and the internet on the right-hand side, and how it just takes one device that's infected to basically come through and basically infect the entire network. MEC stands for multi-edge. So that's multi-edge communication applications in this environment of edge cloud computing, where device-to-device communication, there's 75 billion devices we're going to have in 5 years. You can basically bring the entire network down. And the example has been given already tonight of coronavirus and that tragedy that we're currently facing. And of course, with malware, these kind of things equally spread very fast, perhaps even faster than the coronavirus has been spreading. So these are the kind of threats that we're going to have to be dealing with from devices going forwards without sufficient security being on them that can basically go in and take down the entire network. Now, it's pointed out that 5G networks are going to have more encryption on them relative to, say, 4G and other networks. However, there are two limitations with that. One, devices are also communicating with 4G and 3G networks, right? It's going to take time before we get everything onto a 5G network. And those networks have less encryption on. The other thing is, if the devices, you're only as strong as your weakest point, as you know from being cybersecurity experts, or those of you cyber experts. You're only as strong as your weakest link. And therefore, if the device has insufficient security on it, you can then bring down the entire network, but with it spreading malware through the whole system, through the whole network. I'm going to talk a little bit about federated learning. It's a technique we use. It's a new technique of machine learning that came in about 2017. And in this era of cybersecurity and GDPR, we have kind of like conflicts in a way. We have to protect data privacy, data security, and the serious fines for those breaches. But at the same time, we want to deploy machine learning to improve personalized experiences and learn from the data and collaborate across, customers, etc. Federated learning is a type of machine learning where you start with a global model and you can actually deploy that across multiple devices and personalize the learning on the device and then aggregate back at a generalized level. So here's the steps to federated learning. You start with an initial global model at time t0. That gets deployed, say, onto all these mobile devices. The devices don't share data. The data stays on the device. So you keep data security, you keep data privacy. But then the devices update, they pull together back to a global model, excuse me, with the learning. And when I say the learning, that's from a machine learning standpoint, the gradients, updating gradients and updating weights in the model. And that update gets aggregated and then redistributed back to these devices. So it's a circular system. We put encryption on at this level of the devices so that you can't get adversarial attacks. And we'll go a bit more into adversarial attacks because they've been mentioned tonight to explain what they actually are and how they work. And that limits the scope of adversarial attacks to get back in and try and reverse engineer what the data might be on this device. So that's a way basically of enhancing both the personalized learning on the device, but also finding if there's malware there early and kind of like detecting that new malware and kind of immunizing the whole system, redistributing, updating the learning across all the devices. So I think this pretty much shows the same thing here that was being shown on the previous slide, that you've got this scale for aggregation. And of course, mobile devices, many of them are going to have AI chips on them going forwards. The types of machine learning that we can use for cybersecurity can be supervised and unsupervised. Supervised learning is used mostly out there in machine learning in general, and that's where we label something. For example, if we use computer vision, an orange or a lemon, and then we train the algorithm to understand that. And then there are also techniques known as classification, regression, and clustering. And clustering often gets more used with unsupervised learning, where you let the algorithm learn itself from patterns hidden in the data. Now, regression is based on learning from previous values what the next value might be as per statistics. And classification, and here we're showing an example of classification, where we've trained something, this is malware and this is not malware. And when we get to using machine learning or deep learning in cybersecurity, we're actually going down to the bytes. We're going to binary code, and we're learning at the bytes, at the binary level, what the malware actually looks like, what the patterns are, so the machine learning can actually learn at that binary level, at that binary code level, using both techniques from natural language processing or computer vision and deep learning to understand and learn these malware types and predict them when they occur. So here we're showing two examples, device-to-device attack or device-to-server, and using classification to detect and kind of like immunize the system and try and take care of that along the way. And the kind of devices in this 5G network, laptop, security camera, just for references. This is showing the example of clustering, where you kind of cluster something and it can see something's an outlier, i.e. it's not engaging in normal behavior, and then you analyze the outlier and try and learn whether it's malicious or not. And if it is, you engage in protection. If it's not malicious, you learn from that, and then the machine learning will learn to classify, learn to treat it as non-malicious going forwards. Now, coming back to the 5G network, an important part of the 5G network is a process known as network slicing. And what network slicing actually does is it's going to allow the network to be virtually partitioned into slices. So you can sub-partition the network to a client, for example. It could be a hospital, for example. It could be a corporate enterprise like BMW or Jaguar, or a pharmaceutical company like Glaxo. And what we're doing essentially is we're reserving part of the network for different types of services, which in the 5G, as Richard pointed out, we're going to have more types of services like augmented reality, virtual reality, IoT, machine-to-machine communications with those faster speeds and lower latencies that 4G currently struggles with will work under 5G. Now, with network slicing, you can sub-partition the network virtually to individual clients, corporate clients, etc., or even hospitals, healthcare providers for these different services. So physically, it's actually one network, but virtually, it's the enterprise client is seeing different services through the network, which are under service level agreements are reserved. Now, the problem for cybersecurity is that, or for the client, is again, if you're only as strong as your weakest link in the chain. And if you have here, say in the mission critical IoT slice, a device that has weak security on it coming here and infecting something, it can go through and knock down the entire network and spread everything through the whole network. So again, getting to powerful device security is going to be a key thing, and that's why we're proposing federated learning as a way to learn on the device, have the AI active on the device in an edge scenario, learn through all the devices and aggregate that learning back at a global model and keep on distributing that out there. So that it's like an immunization system that you keep on updating as new malware occurs. As we've seen with coronavirus, a new virus comes out, it starts impacting and starts spreading quickly. Again, the ability to detect new things and update the whole network for that through federated learning. I'm going to talk quickly about GANs and deepfakes because they've been mentioned tonight, and I just thought I'd try and explain them. So just for want of explaining how they work for the wider community, and they are a big area going forwards in cybersecurity. Now what you have is you actually have two neural networks with deepfakes, or GANs if you like, and you have a discriminator and a generator. The generator is creating the fake images, and the discriminator actually is showing the real and fake image at the beginning. The generator starts with random noise. It doesn't know what the real image really looks like, and it keeps on creating it. Here you see the number 8 is the example, and the discriminator keeps on giving it feedback. This image is good, this image is bad, criticism, until the generator creates such a good fake image that the discriminator is fooled. So it's like a fraudster, you know, and a master, if you like, and the fraudster keeps on getting good enough. You know, you've got a banker here who knows what the real banknote looks like, and the fraudster keeps on getting so good through the constant criticism until it knows how to create that really good fake banknote that even the expert discriminator gets fooled. So this is what the network actually looks like. So it's two neural networks competing with each other. It's competition, mini-max competition, until the fake image is so good that the discriminator can't discriminate between what's fake and real. And at that point, that's when the GAN has done its job. Now, it does have genuine uses. I say genuine, you know, in an entertainment sector and other things, where you can start to create artwork has been created in gaming scenarios, artificial videos. But unfortunately, as pointed out, it also can be used for creating fake things. We actually use GANs. Well, we've used them for creating synthetic molecules. They're being used in drug discovery by in silico medicine and other de novo drug companies to create, when you're creating molecular compounds through smiles, synthetically, and then using them for testing to create new drugs, which hopefully will help in the fight against coronavirus. So they do have legitimate use cases. Now, these are actually the kind of things that GANs spit out. These are all fake. These are all fake images. None of these people actually exist, but you can see they look very real. This is our own GAN, actually. This is Tanya, who's in our team here on the left, one of our machine learning engineers. And here she's artificially, you can see it looks a bit like her, and as you go to the right, it's becoming less and less like her. So this is actually an output of our own GAN. And now, where GANs get used, adversarial learning can be used to trick machine learning. Is, for example, when you're training a deep neural network, and you're, as explained, garbage in, garbage out. So if you're training something, this is a lemon, this is a apple, but you could be doing it for a self-driving car and object detection. This is an ambulance, this is a fire engine, or, you know, this is an ambulance, this is a pedestrian, and adversarial attacks go in and spoof, and they're getting, without the algorithm, the model knowing, or without the human machine learning engineer knowing, and putting fake images there, mislabeled, for example, telling it an ambulance might look like a person, for example. And you might not know that as the machine learning engineer. It's been done without your realizing, and then the deep learning is going to learn something incorrectly and get fooled. So that's the danger with adversarial learning, adversarial attacks, to go in and trick machine learning algorithms. As one example of spoofing. And that's one of the things we have to look out for. So I just thought I'd give that quick deviation because it was mentioned before. This is what GANs are. That's how adversarial attacks actually work. No, going back, sorry, I've got a typo here. That should actually say 5G, not percentage G. But this is what machine-to-machine communication is actually going to look like in the real world going forwards when we get to autonomous cars out there. They're going to rely on communicating with each other. You know, autonomous car is not going to work in isolation. It's going to have the AI on the car itself, on the connected car, and they're going to communicate with each other so that they make optimized decisions together. So you see this car at the front is broken down, and the computer vision, the deep learning on it is telling each car behind it, even though this one here can't see this broken down car at the front, but it's through the chain, they've all told each other. So machine-to-machine communication. So in the cybersecurity world, if you can get in with adversarial attacks and trick and fool, then of course you can create chaos through the whole network, unfortunately. So these are the kind of things that we need to make sure that we immunize for going forwards, or avoiding. This is actually from GSMA, and it shows in the 5G cybersecurity world, in a smart city example, the number of connected devices that are going to rely on machine-to-machine communication and across 5G networks, and the scope for vulnerability. The scope for attack is huge, and I think Microsoft always give the example. They've got their training data set, which many of us train on in machine learning for cybersecurity, and that's Windows. There's 40 million lines of code on it, and they say the average developer, I'm a developer too, we all like to think we're invulnerable and we don't make mistakes, but in production code, every 1 in 2,500 lines of code has an error on it. 1 out of 2,500, according to Microsoft, will slip into production. Now, of course, I would like to say I'm invincible and perfect, but we all like to think that, but that's the reality. Microsoft Windows is 40 million lines of coding. So you've got these attackers, adversaries going in, trying to find these weaknesses that have slipped into production and poking all the time to find these attack spaces. So you can see the kind of areas that, apart from connected cars, the healthcare network, there's already been a repeat alleged attack whilst coronavirus has been in the headlines on the US Department of Health, a cyber attack, I think 4 or 5 days ago. Fortunately, they've managed to immunize that, but it shows that we have to be constantly on our toes. In this 5G world, it's going to create huge, vast opportunities with machine-to-machine communication for automation, automating our retailers, automating, we're relying on online delivery, for example, in many cases in the midst of the coronavirus network issue. We're also relying upon video conferencing for this event that Richard has kindly hosted. So again, the scope to come in and knock down the entire network now is huge, unfortunately, as we're relying on the virtual services. We need to consider the scope to identify the vulnerabilities and shut them off going forwards. The healthcare network, as mentioned, hospitals are going to be inundated, unfortunately, as we've seen with Italy and elsewhere in China, to make sure that we can, these critical services that are going to be provided with ventilators, etc., don't get compromised. Traffic systems going forwards, as we get to smart traffic networks, the scope for a device to infect the entire network and spread that around, spoofing attacks, etc. Just the vulnerabilities threatscape is huge. Now, the huge opportunities to automate and bring services out there, but at the same time, sorry, this is a bit generic, but we really need to understand and plan ahead for these so that we can, and we personally believe in our team that federated learning is going to be fundamental in bringing security across the network and putting that onto device, learning across the devices, and then aggregating that and pooling it, collaborative learning, and collaboratively sharing that learning so that we can constantly update the system, be it whether the device is an autonomous car, a connected device in a healthcare system, or an insurance device, etc. Collaborative learning to constantly update and learn of new malware attacks and spread that information through the system as fast as possible is basically what we're trying to do in our approach, and we believe that's going to be fundamental in this new era that we move into going forwards. And I think at this point, I'm probably going to hand it over. I've tried to keep this more generic rather than going into a lot of detail, but if you want me to go into detail on the code side, happy to do that too.